We're doing statics today. Statics is just a branch of physics that deals with problems um, involving equilibrium. So, our outline for this presentation is first, we'll talk about the various conditions for equilibrium, which we actually already talked about in a previous video. And then we proceed directly to the sample problems. So for an object to be truly in equilibrium, whether static or dynamic, then it must obey the following conditions. First, that the sum of all forces should be equal to zero, and that the sum of all torques acting on the rigid object must be equal to zero. But this first equation is actually um, three different equations. That the sum of all the x components is equal to zero, and the sum of all the y components of the forces is equal to zero. And if it is a force that acts on the three-dimensional plane, um, that the sum of all forces along the z must also be equal to zero. So let's dive right into some of these problems. This one I got online. Two children are balancing a seesaw with negligible mass. The first child has a mass of 26 kilograms and sits 1.6 meters from the pivot. So if the second child has a mass of 32 kilograms, how far is she from the pivot? And what is FP, the supporting force exerted by the pivot? It's called, it's pronounced pivot, last time I checked. But you can also just call it pivot if you want. So before anything else, class, I would like to introduce to you system schema. And what a system schema is just a way of visualizing all the forces that are acting in our system. In our system, in this case, is the seesaw, the fulcrum, and the earth. So, and the two children are also a part of our system. So, to create a system schema, um, and we're doing this again because we want to know all the forces that are acting in the system. Before we do the free body diagram, which I know most of you are familiar with, we have to create a system schema. And from now on, I will require you to do this. So a system schema is just you're listing down all the objects in your system. And let's just draw a circle and then like for the boy, what are the objects in your system? We have the girl, and sorry for the dogs. We have a seesaw, and then and we have the fulcrum, or is that a pivot? And of course we have the earth, right? So you're just really writing down all the objects in circles, and then you connect these objects and figure out what the force between them is. For example, so the boy and the seesaw. So the boy is sitting down on the seesaw. So actually, there is a normal force. It's called the normal force. It's the boy's behind is sitting on the seesaw, so the boy's behind is pushing on that part of the seesaw, but at the same time, that boy is also that seesaw is also pushing upwards on the boy. So there's a normal force between the boy and the seesaw, and there's also normal force between the girl and the seesaw. And we know that the seesaw is sitting on top of the fulcrum, and we know let's call it the normal force. But in this case, in this problem, he specifically labeled the normal force that the fulcrum acts on the seesaw as the FP. So maybe we just call this FP. And then how about the boy and the earth? Actually, everything else here, they're all, the boy is acted on by the earth. So we call that Fg, or gravitational force, or the weight. And also the girl is also acted on by the earth, call it the weight. And it was not mentioned here in this problem, but actually this seesaw it has negligible mass. So whenever you have yeah, it was mentioned pala. So that means that the seesaw is not interacting with the earth, strangely enough, because the only way for gravity to act between two objects is if the object has mass, if the two objects have mass. So apparently the seesaw has negligible mass, so there is no interaction with the earth with it. Maybe there is, but it's too tiny and negligible, so we don't have to write that down. Fulcrum I will not connect because, well, it's really connected to the earth here, and although I would say that it is a part of the earth because it's connected to the earth. So we're really focusing right now on the boy seesaw girl, and so I am going to draw dashed lines around the boy seesaw and girl. And then we'll look at all the external factors acting on the boy seesaw and girl. And what those forces are, they are the ones that extend outward away from the dashed lines. And as you can see, this right here is an external force because it goes beyond the dashed line. And the FP is also an external force acting on our boy seesaw girl system because it extends away from the dashed line. And also the weight of the girl extends beyond the dashed line, so it is an external force acting on our boy girl seesaw system. Now Fn, the normal force between the boy and the seesaw and the girl and the seesaw, they are what you call internal forces. And we're not concerned with internal forces. They are within the system, but we are not concerned with that. Okay, so we now have a boy seesaw girl system, and now we can create now a free body diagram. So a free body diagram is, in this case, is for a rigid object. If you remember in your previous lessons, some free body diagrams, you approximate the object to be just a point, but we cannot afford to do that with a rigid object because a rigid object is not a point. So we need to, this is make it an extended rigid object and not just a point, because the location of these forces matter. So this is our boy seesaw girl. Actually, we still simplified the boy seesaw girl into a kind of a rectangular shape. And this is our boy seesaw girl BSG system. And we're looking at the forces acting on that system, in particular the external forces. So we go back to our system schema and we find that there are three external forces acting on our system. And we have to be very specific about where these forces are acting on our system. We know that the weight of the boy is acting to the left of the system, to the left of our rigid extended object, and it's actually called weight 1 or FG1. and that the weight of the girl is acting downward, weight 2, FG2, and acting on the middle is the normal force that the fulcrum exerts on our system, but we call that FP because that's what's written here in the problem. And so, if the second child has a mass of 32 kilograms, how far is she from the pivot? So, what's unknown is this distance from FP to W2. And we also know that, right, that's the only thing. We also know that this distance here is 1.6 meters. Now, this system is in equilibrium, so I'm just going to write down the conditions for equilibrium. The sum of all torques is equal to 0, and the sum of all forces along the x is equal to 0. The sum of all forces along the y is equal to 0. I'll not even bother writing sum of all forces along z because this seems to be a two-dimensional problem, not a three-dimensional one, which is pretty common in basic physics. We start off with two-dimensional problems. So how far is she from the pivot? So we are going to start this problem with using this equation, summation of torques equals 0. And when we are trying to describe the torques in this system, remember that torque is actually two formulas, no? The moment arm times F and magnitude of the angular position, force, sine theta, the short angle between R and F, and n hat. Or you can also do the matrix, right? So all these four formulas involve R, either the angular position or the moment arm, and F. So in order to define the torques that are acting in this system, we need to define the R's for each force. So we know the forces, omega 1, weight 1, W1, W2, and FP. We now have that part of the equation. But what are their corresponding R's? What is the moment arm for W1? What is the moment arm for FP? Or what is the moment arm for W2? Or what is the angular position vector for W1 or FP or W2? But in order to define the R for each force, we need to know where the axis of rotation is because R is measured from the axis of rotation. Now, what I'm about to say right now is important, so listen carefully. It doesn't matter where you define your axis of rotation to be in an equilibrium condition. So when an object is in equilibrium, you can choose anywhere in this extended object where you want your axis to be, and it doesn't matter. You will always get the same result. And I think it makes sense because the object will not have an angular acceleration anyway, it will not rotate anyway. So it doesn't matter where you define or where you place your axis of rotation is. Now, that opens up possibilities for strategic methods of where you need to place your axis of rotation. And strategically speaking, the best place where you want to put your axis of rotation is where it hits a force that is kind of vague that you don't know much about. Because when you place the axis of rotation there, the effect, the torque effect that that force produces becomes zero because then R becomes zero for that particular force. What I mean is, I'm actually gonna choose the axis of rotation here by labeling X because I don't know much about FP for now. So by actually putting the axis of rotation here, And it does seem to make sense to put it here, right? Because the fulcrum is here in the middle, but that's not really the reason why we're putting the axis of rotation here. Let me reiterate, we can choose wherever we want our axis to be. But the main reason why I put my axis in here is because I want this FP, the torque produced by FP, to disappear because I don't know much about FP. I know W1, I know W2, right? But I don't know much about FP. So I want that torque produced by that FP to disappear because then RP is zero because it is where the axis of rotation is. So I'm gonna go to summation of torques equals zero. And now we have three forces acting torque. The torque produced by W1, the torque produced by FP, which I mentioned is now zero, but I'm just going to write that anyway, and the torque produced by W2 is equal to zero. Now I left space in between because I want you to think about, like, does this torque produce positive, does this force produce positive torque or negative torque? Now remember, if that torque produced clockwise rotation, then it produces a negative torque. Or if that force produces a counterclockwise rotation, then it produces counterclockwise, produces positive torque. So let's look at W1. W1, no, I'm trying to, sometimes I have trouble. Now I'm actually looking at a watch. Okay. W1 is actually producing a counterclockwise. Like if no other force exists and only W1 exists, it will tend to cause, through the axis of rotation, this extended object to move counterclockwise. So that's actually a positive torque. FP, I said, is it's gonna produce no torque at all, so it doesn't matter what sign I put here. Let me just write plus. Torque produced by W2, so it's actually making the object rotate counterclockwise. So I'm gonna put that it causes a negative torque, W2. Okay, so now what formula should we use? Actually, we can actually use any of the two. And we can even actually use that matrix, but I think it's overkill if we do that. So let me just use this moment arm formula because we know that this one is R1, R moment 1 arm, and this one is R moment arm 2. And I know that it's a moment arm because it is, a moment arm is the distance that is perpendicular to the line of action of the force. And as you can see, omega 1 and R moment arm 1 are perpendicular. So I can just use the formula. So R moment arm 1 W1 and 0 ang TFP because it doesn't have R and minus R moment arm 2 omega 2. No, not omega, W2. I'm always confused. So how far is she from the pivot? So we're actually looking for R moment arm 2. So I'm gonna put that, I'm gonna do something here. R moment arm 2 omega W2 equals R moment arm 1 weight 1. So therefore, R moment arm 2 is equal to R moment arm 1 weight 1 over weight 2. So now I'm ready to solve to R moment arm 2. R moment arm 1, that is 1.6 meters. weight 1 is just 26 kilograms times 9.8. Remember that kilograms is not weight, that's mass, but we have to multiply it by g to make it weights. And but it seems like it doesn't matter because 9.8 will just cancel out with the denominator. So this is gonna cancel out. It becomes just a matter of the masses and the distance. I have a calculator here, and let's hope I get 1.3 meters because that's what it says at the bottom. And true enough, I get 1.3 meters. It's a fairly easy problem, right? What is Fp, the supporting force exerted by the pivot? So we're asked now to get Fp, and for letter B, what we can do to solve that problem is to use this other condition for equilibrium. Notice that summation of Fx doesn't play a role in this problem because there are no forces along the horizontal. So this is what I do for this. I actually do this Fp j hat because it's directed along the positive y-axis plus W1 negative j hat because it's directed along the negative y-axis, W2 negative j hat because it's directed along the y-axis as well is equal to 0. But all the j hats cancel out. If you divide both sides by j hat, you are left with just the magnitudes of the forces and what sign they are left with. So some people just go to this recent step immediately, but I like to put the j hats there just to guide me. So therefore Fp is just weight 1 plus weight 2. And the weight 1 is 26 times 9.8 plus 32 times 9.8, and you will get 568 newtons. Okay. What if the seesaw, this is the last part of the video, what if the seesaw has mass? Now, or maybe let's do that in the next video. Okay, so thank you.